To solve another Leetcode problem, 1245, tree diameter. So the diameter of a tree is the number of edges in the longest path in that tree. So for example, the diameter of this tree is going to be 2 because it's the longest path. So this is one edge, another edge, it's going to be 2. That's just a secondary example. So in this example, the longest path is going to be, let me make it clear. So the longest path is going to be 4, as you can see, from here to here, there are 4 edges, so it's going to be 4. So we are going to return the longest path inside of the tree. Yeah. So there is an undirected tree of n nodes, so it is labeled from 0 to n-1, and we are giving a 2D array edges. Yeah, so where the edge is less is n-1, because it is a tree structure, it is okay, and the ends I is ai, bi, indicates there is an undirected ends between nodes ai and bi in the tree, so this is also okay. Yeah, we just need to return the diameter of the tree. So definitely there are 2 ways to solve it, DFS and BFS. Yeah. So today I'm gonna use BFS to solve the problem. Basically, I think BFS is much easier. Although DFS can be solved, but it's a little bit difficult to write. You have to analyze, a lot of things. Otherwise, you're gonna make a mistake. And for BFS, basically we're gonna use topological sort to solve the problem. Yeah, but let's just try to understand how can we use the topological sort to solve it. I'm gonna make a drawing from maybe here. Yeah. So I'm gonna use the second example as our drawing. So we have something like this. So this is a undirected graph, and it is connected like that. Yeah. So according to the edges, definitely we can build an undirected graph. We can use adjacency list to build this kind of graph. Yeah, and we are going to use BFS to solve the problem. And the topological way is that we're going to check all the children of the nodes. We're going to check all the children, all the leaf nodes first. I mean all the children first. So for example, we're going to check all those ones first, and this one, and this one first. And we're going to check layer by layer until we find the root node. Yeah, because currently we don't know which is the root node. So this is one layer, and this is another layer, and then we find the root node. So how many layers? We find 2 layers, and there's only 1 root node left. So it means the diameter is going to be 2 times 2. But what if there are 2 nodes left behind? So let me remake the drawing a little bit. So we're going to use this kind of structure. Yeah. So it is connected like that. After the first layer and second layer, we have 2 nodes left behind. So how many? What is the diameter? It's going to be 2 times 2 plus 1. Yeah. So this is the formula. So let's just remake the drawing to make it another one. So definitely, so definitely, what we're gonna use the BFS. Yeah, because definitely for a tree structure there must be a longest path. We are not sure, but definitely there is. Yeah. So what we're gonna do? We're gonna check layer by layer. So outside these areas, this gonna be the first layer. So this one, and this one gonna be the first layer. And then we're gonna check the second layer. It means we have a second layer. Yeah. And now we're gonna find this one. Yeah. If we can find this one, definitely this is gonna be the root. Yeah. And we can check the result. Maybe you think, maybe what about another case? So for example, it is like that. Yeah. So how can we check the longest path? It is also the same. Definitely, it is not the diameter is not 2 or 2. It is 3. But how can we do that? We're gonna check the outer layers. So those 2 nodes are the outer layers. This is one layer, and then we're gonna find our target because there are only 2 nodes left. Yeah. So if there are 2 nodes left, so definitely, and we can check the result. So it's gonna be 1 times 2 plus 1. So it is 3. How can we do it like that? We can use a topological sort because this is the leaf node, and we're gonna take out this one, and then we take this one, and get our final result. Yeah. I think now we are clear about how to solve it. We can just write the topological algorithm to solve the problem. But it is an undirected graph. We have to be careful about it because it is a little bit different from a directed graph. Yeah. So I'm gonna prepare J and integrate. So it's gonna be a default index, and inside it's gonna be list, and integrate it's gonna be 0 times. Yeah, let me just check the so the integrate gonna be 0 times the number of the edges, so length of the edges plus 1. Now we are going to check the edges of the graph. So for AB in edges, we don't need to reverse because it is an undirected graph. It is okay. We just need to build it. So for GA dot append B, and with GB dot append A, and similarly for the integrate A should plus equal to 1, and integrate B should plus equal to 1. We just build an undirected graph, and we need to prepare all the integrate and the graph. Now we're gonna prepare the queue. So we have to be careful about this queue because it's gonna be a little bit different from the directed graph. So for IV in enumerate the integrate, we have to check if this v equal to 1 because it is directed. So for example, the first layer is going to be 0, 3, and 5 because it is undirected. It should be undirected because it is undirected. So the integrate, so for this 0, 3, and 5 should be a 1 instead of 0. So this is why we're going to check if v equal to 1. Yeah. Now the queue is okay, but we need to check the depth. I'm going to prepare a depth, and let me think if there's anything else we needed to do. Maybe not. So I'm going to prepare a depth. I'm going to starting from 0. Yeah, later on I'm gonna save it, and my result gonna be I'm gonna set it as a 0. Yeah. Now I'm gonna check this queue. So while queue, so node equal to q dot pop left. So this is the topological structure, and I'm gonna check the neighbor, and I'm gonna check the integrate. So for the integrate with this neighbor, so the minus equal to 1, I'm going to check this integrate with this neighbor. If it is equal to currently, it's going to be 1 instead of 0. Otherwise, you're going to get this wrong. Yeah, because this is an undirected graph. If you make it 0, there's going to be so while you are looping through the graph, it is not like the topological structure. While you, for example, if you after you put a 0, 2, 4 inside, and then you check this 1, and for the next loop you're gonna put a 0, 2, 4 inside again because if it is equal to 0. So you have to set it to be 1 because it is an undirected graph. Now we're gonna put it inside the queue. We're gonna put the neighbors inside the queue. Yeah, I suggest you're gonna try to use some examples to check. If you're gonna use a 0, what's gonna happen? So for example, for the first example, the strange thing is gonna happen. Now I think I've already put everything here. Yeah. But for me, I want to check how many layers basically. So this means I need a for loop from here to check the layers. So for underscore in range and length of the queue, I'm gonna pop it out and put it inside according to the topological BFS structure of the coding. And after that, for my depth, I'm gonna plus equal to 1. Yeah. So currently I think it is okay, but I didn't prepare my result. Yeah. So actually I need to have a result because I needed to record what is my final node. Maybe there's only 2 nodes left behind, or maybe there's only 1 node left behind. I need to check that because 1 is different from 2. Yeah, because it is not fixed. If it is fixed, it is okay. I mean, after taking out all the layers, there's only 1 node left behind, or maybe there are 2 nodes. In this example, 1 node left behind, but in another example, maybe like this. Yeah, it is a 2 node left behind. We take out this one. There are 2 nodes left behind. Yeah. So this means we're going to use a result to record how many nodes are left behind. Yeah. So let me check. So from here, I'm going to record this result. So it's going to be length of the queue. Yeah. Basically, this is about checking how many nodes left behind while I'm using the BFS. But for the depth, it's going to be plus 1. So for example, let's just check this example. First of all, we're going to check this 3 and 5, okay? And we're going to have a depth plus 1. So it means it is 1. And then we're going to check 2 and 4. So it is 1 plus 1, it is 2. Right? Yeah, but then we're going to check this node 1, it's going to become 3. But 2 times 3 is going to be wrong. So for me, I'm going to start the depth as -1, because if I set it as -1, so finally I'm going to get a 2. Yeah, and then I can only I only need to check if there's only 1 node left behind or 2 nodes left behind. So I would to set a depth as -1 from the beginning. I just need to simplify my calculations for the depth. Finally, I think I can return the result. But what if there's only 1 node? So for example, we have a node, only 1 node left behind. What if there's only 1 node? For example, it is a node 0. So what is the so for this node 0, what is the depth? There's only 1 node 0. So the depth is going to be, the diameter going to be 0 because there's no edge. There's only 1 node. Yeah. So this means we're gonna need to check the result, because the result can be 1 or 2, but it can also be 0. If this result is 0, why it is 0 not 1? Because I have 1 node. Yeah. This is because according to our algorithm, so if we didn't put anything inside of queue, if there's only 1 node for an undirected graph, so our integrate is going to be 0. So there will be nothing inside of queue. If there's nothing inside of queue, so the result will not be updated, so it's going to be 0. So if this result is 0, definitely we're going to return a 0 first. Yeah. So if this result equal to 0, so we're going to return a 0. So otherwise, we're going to return depth times 2 if result equal to 1, else if this result equal to 2, so it's going to be depth times 2 plus 1. Yeah. Now let me run it to check if it works. As you can see, it works. Yeah. Now let me submit it to check if it can pass all testing cases. As you can see, it's pretty fast and it passes all testing cases. This is because we are using the best algorithm, I believe, to solve the problem, because it is a topological sort, and the time complexity is only E plus V. E is the number of edges, and N is the number of vertices. So basically, it is the ON time complexity. Yeah, I think that's for today's problem. Thank you for watching. See you next time.